Hello and welcome back. I'm your friend in Saxo. Today we're going to know the section complex numbers. I guess you already know what the complex number is, but we're still going to explore this topic for a little bit.
Move the orange dot to -2 plus 2i. So we have a complex number here. It has a real part, -2, has an imaginary part. You have 2 times I. And what you see here is we're going to plot it on this kind of two-dimensional grid, but it's not our traditional coordinate axes. In our traditional coordinate axis, you're plotting a real x value versus a real y coordinate. Here, on the horizontal axis, that's going to be the real part of our complex number, and our vertical axis is going to be the imaginary part. So in this example, this complex number, our real part is the -2, and then our imaginary part is a +2. And so that right over there in the complex plane is the point -2 plus 2i. Let's do a few more of these. So 5 plus 2i, once again, real part is 5, imaginary part is 2, and we're done.
Okay, so you can indeed represent your complex number with two-dimensional plane. For example, this one as the x-axis as a real part number and the y-axis as the imaginary part of that number. Then the distance and the midpoint of complex numbers. What is the distance and the midpoint? I have no idea about that. I mean, I indeed know the distance and the midpoint, the two concepts, but I don't know how it can be related with the complex numbers.
So we have two complex numbers here. The complex number z is equal to 2 plus 3i, and the complex number w is equal to -5 minus i. What I want to do in this video is to first plot these two complex numbers on the complex plane, and then think about what the distance is between these two numbers on the plane, and what complex number is exactly halfway between these two numbers, or another way of thinking about it, what complex number is the midpoint between these two numbers. So I encourage you to pause this video and think about it on your own before I work through it. So let's first try to plot these on the complex plane. So let me draw, so right over here, let me draw our imaginary axis. So our imaginary axis, and over here, let me draw our real axis right over there. And let's see, we're gonna go as high as +2 in the real axis and as low as -5 along the real axis. So let's go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And along the imaginary axis, we go as high as +3 and as low as -1. So we could do 1, 2, 3, and we could do 1, 2, 3. And of course, I could keep going up here just to have nice markers there, although we won't use that part of the plane. Now let's plot these 2 points. So the real part of z is 2, and then we have 3 times I. So the imaginary part is 3. So we would go right over here. So this is 2, and this is 3 right over here. 2 plus 3i. So that right over there is z. Now let's plot w. W is -5. 1, 2, 3, 4, 5. -5 minus I. So this is -1 right over here. So minus I, that is w. So first we can think about the distance between these two complex numbers, the distance on the complex plane. So one way of thinking about it, that's really just the distance of this line right over here. And to figure that out, we can really just think about the Pythagorean Theorem. And if you say, hey, what about the distance formula and in 2 dimensions? Well, that's really just an application of the Pythagorean Theorem. So let's think about that a little bit. So we could think about how much have we changed along the real axis, which is this distance right over here. This is how much we've changed along the real axis. And if we're going from w to z, we're going from -5 along the real axis to 2. What is 2 minus -5? Well, it's 7. If we go 5 to get to the 0 along the real axis, and then we go 2 more to get to 2. So the length of this right over here is 7. And what is the length of this side right over here? Well, along the imaginary axis, we're going from -1 to 3. So the distance there is 4. So now we can apply the Pythagorean Theorem. This is a right triangle. So the distance is going to be equal to the distance. Let's just say that this is x right over here. X squared is going to be equal to 7 squared. This is just the Pythagorean Theorem, plus 4 squared, Or we could say that x is equal to the square root of 49 plus 16. I'll just write it out so I don't skip any steps. 49 plus 16. And what is that going to be equal to? That is 65. So x, that's right. Yeah, 59 plus another 6 is 65. X is equal to the square root of 65 65. And let's see, 65, you can't factor this. There's no factors that are perfect squares here. This is just 13 times 5, so we can just leave it like that. X is equal to the square root of 65. So the distance in the complex plane between these two complex numbers, square root of 65, which is, I guess, a little bit over 8. Now, what about the complex number that is exactly halfway between these two? Well, to figure that out, we just have to figure out what number has a real part that is halfway between these two real parts, and what number has an imaginary part that's halfway between these two imaginary parts. So if we had let's say that some complex number, let's just call it A, is the midpoint. Its real part is going to be the mean of these two numbers. So it's going to be 2 plus negative 5, 2 plus negative 5 over 2, and its imaginary part is going to be the mean of these two numbers. So plus 3 minus 1, 3 minus 1 over 2 times I, and this is equal to, let's see, 2 plus negative 5 is negative 3. So this is negative 3 halves, plus this is 3 minus 1 is negative 2 over 2 is, let's see, 3 minus, let me make sure I'm doing this right. 3, so I'm taking the mean. 3 minus 1 is 2, divided by 2 is 1. So 3 plus 3, negative 3 halves plus I.
Okay, I got it. So it has nothing different than the traditional calculation. It has no different than that. If you want to get the midpoint, you add them up and divide it by 2. If you want to get the distance, you use the Pythagorean theorem. Then what's the complex conjugates and dividing complex numbers? This is hard to read.
Complex conjugates and dividing complex numbers.
I want to make a quick clarification and then add more tools in our complex number toolkit. In the first video, I said that if I had a complex number z and it's equal to a plus bi, I used a word, and I have to be careful about that word because I use it in kind of the everyday sense, but it also has a formal reality to it. So clearly the real part of this complex number is a. Clearly that is the real part. And clearly this complex number is made up of a real number plus an imaginary number. So I, just kind of talking in everyday terms, I called this the imaginary part. I called this imaginary number the imaginary part. But I want to just be careful there. I mean, I did make it clear that if you were to see the function, the real part of z, this would spit out the a. And the function, the imaginary part of z, this would spit out, and we talked about this in the first video, it would spit out the number that's scaling the I. So it would spit out the b. So if someone is talking in the formal sense about the imaginary part, they're really talking about the number that is scaling the I. But in my brain, when I think of a complex number, I think of it having a real number and an imaginary number. And if someone would say, well, what part of that is the imaginary number, I would have given this whole thing. But if someone says just what's the imaginary part, or they give you this function, just give them the b. Hopefully that clarifies things. Frankly, I think the word imaginary part is badly named because clearly this whole thing is an imaginary number. This right here is not an imaginary number. It's just a real number. It's the real number scaling the I. So they should call this the number scaling the imaginary part of z. Anyway, with that said, what I want to introduce you to is the idea of a complex numbers conjugate. So if this is z, the conjugate of z, it'd be denoted with z with a bar over it. Sometimes it's z with a little asterisk right over there. That would just be equal to a minus bi. So let's see how they look on an Argand diagram. So that's my real axis, and then that is my imaginary axis. And then if I have z, this is z over here. This height over here is b. This base, or this length right here, is a. That's z. The conjugate of z is a minus bi. So it comes out a on the real axis, but it has minus b as its imaginary part. So just like this. So this is the conjugate of z. So just to visualize it, it really is, the conjugate of a complex number is really the mirror image of that complex number reflected over the x-axis. You can imagine if this was a pool of water, we're seeing its reflection over here. And so we can actually look at this to visually add to add the complex number and its conjugate. So we said these are just like position vectors. So if we were to add z and its conjugate, we could essentially just take this vector, shift it up here, do heads to tails, shift it up here, do heads to tails. So this right here, we are adding z to its conjugate. And so this point right here, or the vector that specifies that point, is z plus z's conjugate. And you can see right here, or just visually, this is going to be 2a. This is going to be 2a. And we could do that algebraically. If we were to add z, that's a plus bi, and add that to its conjugate, so plus a minus bi, what are we going to get? These two guys cancel out. We're just going to have 2a. Or another way to think about it, and really we're just playing around with math, if I take any complex number, and to it I add its conjugate, I am going to get 2 times the real part of the complex number. Oh, and this is also going to be 2 times the real part of the conjugate, because they have the exact same real part. Now, with that said, let's think about where the conjugate could be useful. So let's say I had something like 1 plus 2i divided by 4 minus 5i. 4 minus 5i. So it's no real obvious way to simplify this expression. Maybe I don't like having this I in the denominator. Maybe I just want to write this as one complex number. If I divide one complex number by another, I should get another complex numbers. But how do I do that? Well, one thing to do is to multiply the numerator and the denominator by the conjugate of the denominator. So 4 plus 5i over 4 plus 5i. And clearly, I'm just multiplying by 1, because this is the same number over the same number. But the reason why this is valuable is if I multiply a number times its conjugate, I'm going to get a real number. So let me just show you that here. So let's just multiply this out. So we're going to get 1 times 4 plus 5i is 4 plus 5i. And then 2i times 4 is plus 8i. And then 2i times 5i, that would be 10i squared, or negative 10. And then that will be over. Now, this has the form a minus b times a plus b. So that's the product of, a plus b times a minus b is a squared minus b squared. So it's going to be equal to 4 squared, which is 16, minus 4 squared. Oh, why did I have 4 plus 4i here? This would be 4 plus 5i. What am I doing? 4 plus 5i. The same number over the same number. And this was a 10 right over there. This is the conjugate. I don't know, my brain must have been thinking in 4s. So obviously, I don't want to change the number 4 plus 5i over 4 plus 5i. So let's multiply it. This is a minus b times a plus b. So 4 times 4. So it's going to be 4 squared minus 5i squared. 4 squared minus 5i squared. And so this is going to be equal to 4 minus 10. Let's add the real parts. 4 minus 10 is negative 6. 5i plus 8i is 13i. Add the imaginary parts. And then you have 16 minus 5i squared. Well, 5i squared, I squared is negative 1. 5 squared, so it's going to be negative 25. The negative and the negative cancel out. So you have 16 plus 25. So that is 41. So we can write this as a complex number. This is negative 6 over 41 plus 13 over 41i. We were able to divide these two complex numbers. So the useful thing here is the property that if I take any complex number and I multiply it, by its conjugate, and obviously the conjugate of the conjugate is the original number. But I take any complex number and I multiply it by its conjugate. So this would be a plus bi times a minus bi. I'm going to get a real number. It's going to be a squared minus bi squared. Difference of squares, which is equal to a squared. Now this is going to be negative b squared, but we have a negative sign out here, so they cancel out. A squared plus b squared. And just out of curiosity, this is the same thing as the magnitude of our complex number squared. So this is the neat property. This is what makes conjugates really useful, especially when you want to simplify division of complex numbers. Anyway, hopefully you found that useful.
Okay, so what is the conjugate of a complex number? You just have to use the inverse sign of that imaginary part, and that's all. That's just an concept for the complex number. Then what is this? Identities with complex numbers. Complex numbers and sum of squares. Factorization. What is that?
Long ago in algebra class, we learned to factor things like x squared minus y squared. We saw that this is a difference of squares, and that you could factor this as x plus y times x minus y. And just as a little bit of a refresher, you can multiply these two together and verify that you get x squared minus y squared. In fact, let's just do that for fun. X times x is x squared. X times negative y is negative xy. Y times x is positive xy, and then y times negative y is minus y squared. These two middle terms cancel out, and you're left with x squared minus y squared. What I want to tackle in this video is something that we didn't know how to factor before, and that's the sum of squares. So if we were to factor x, let me do this in a brighter color. If we wanted to try to factor x squared plus y squared, before we knew about imaginary numbers, complex numbers, we didn't know how to factor this. But now that we do, what I want to try to do, and I encourage you actually to pause the video and try to do it before me, is to try to express this as a difference of squares using the imaginary unit I. So let's try to do this. So the first we want to write as the difference of squares. So x squared, we'll just keep as x squared. But now I want to write this part, I want to write the second part right over here as subtracting a square. So I want to subtract a square. So we could write this part as subtracting negative y squared. Obviously, subtract a negative, that's the same thing as adding. Now, how does this help us? Well, this is the same thing as subtracting negative 1 times y squared. Now, if we wanted to write this whole thing as a square, if we wanted to write this whole thing as a square, how would we do it? Well, we have y squared, and what's negative 1 the square of? Well, we know, by definition, negative 1 is equal to I squared, or that I is equal to, or I squared is equal to negative 1. So let's rewrite it that way. So this is going to be equal to x squared minus, instead of negative 1, I'll write that as I squared minus I squared y squared. All I did is I replaced this negative 1 with an I squared. And now this is interesting. I think you see where this is going, but I'll just make it very explicit. This is now x squared minus I y squared. And just like that, using I've been able to write this sum of squares as a difference of squares. And now we can factor it just the exact same way that we factored this original expression. This thing is going to be equal to, so it's going to be equal to x plus this thing, x plus iy, times x minus iy, x minus iy. And we can verify that if you multiply these two expressions together, you're going to get x squared plus y squared. Let's do that. X times x is x squared. X times negative iy is negative I xy. And then iy times x is positive I xy. And then finally, let me do this in a color I'm not using yet. Finally, iy times negative iy is equal to negative I squared y squared. Now, these middle two terms cancel out. I squared is negative 1, and so we have x squared minus negative 1 y squared. So this is subtracting a negative, the same thing as adding a positive, and so this simplifies to x squared plus y squared. So hopefully this now gives you an appreciation of using the complex, the imaginary unit I, how you can actually factor this expression into essentially the product of two complex numbers.
Okay, I guess this video tells us nothing but how can you use the I squared as a number of -1 so that you could almost, let's say, refactor almost any normal real number or real number expression into the complex expression by doing a replacement. For example, here, replace the -1 as the I squared. Again, we get another section. Modulus and argument of complex numbers. What is that?
Modulus, absolute value, and argument, angle, of complex numbers.
So the modulus is just a fancy way for the absolute value, and the argument is the angle. That was complex. So let's get into it.
I have the complex number 3 minus 4. I've plotted it on the complex plane. We see that the real part is 3. We've gone 3 along the horizontal axis, or the real axis. And the imaginary part is negative 4. So we've gone down 4 along the vertical axis. So this right here is the point 3 minus 4i. Now what I want to think about is what the absolute value of 3 minus 4i is. And just as a reminder, absolute value literally means, whether we're talking about a complex number or a real number, it literally just means distance away from 0. So the absolute value of 3 minus 4i is going to be the distance between 0, between the origin on the complex plane, and that point, and the point 3 minus 4i. So this distance right over here is going to be the absolute value of 3 minus 4i. So how can we think about that? Well, we could literally just set up a right triangle and then use the Pythagorean theorem. So let's think about it. If we wanted to set up a right triangle, the height here, well, we went the distance between 0 and negative 4, well, that distance is going to be 4. And then the base of this triangle, the distance between 0 and 3 is just going to be 3. It's going to be 3, and this is definitely a right angle. This is a horizontal line. This is a vertical line. We can now use the Pythagorean theorem to figure out the absolute value of 3 minus 4i, the distance between this point and 0. It's the hypotenuse of this right triangle. So we just use the Pythagorean theorem. This side squared, 3 squared, plus this side squared, plus 4 squared, is going to be equal to the absolute value of 3 minus 4i squared. The absolute value squared. So 3 squared plus 4 squared, that's 9 plus 16, which is 25. So you get 25 is equal to the absolute value of 3 minus 4i squared. 3 minus 4i. And we know if you take the absolute value of something, this is just a distance. It's going to be positive. So we want to take the positive square root, the principal square root of both sides of this. And so we're going to be left with, well, the principal square root, the positive square root of 25 is 5, is equal to the absolute value of 3 minus 4i. 3 minus 4i. So another way of saying it, this thing right over here is going to be equal to 5. This distance right over here is equal to 5. Now, without having to draw it, one way you could just think about this is I'll have my real part, I have my imaginary part. I could literally take each of those parts, square them, take the sum, and take the square root. So another way of taking it, if you didn't want to visualize all of this, but this is really what we're doing, you could say, well, this is just going to be equal to, take the real part squared, take the imaginary part squared. So let me write this. So the imaginary part squared, add them together, and then take the square root. So that's or the principal root. So that's going to be, the principal root is just a positive square root. So that's going to be the square root of 9 plus 16, which once again is equal to 5.
Okay, the absolute value of a complex number is just somehow you apply the Pythagorean algorithm for the real number part and the imaginary number part. That's all. And you can even use it in a reversed way. For example, if you know the absolute value, how can you calculate out the imaginary part of that complex number? Something like that. Let's get into it.
We are asked which of these complex numbers has a modulus of 13. And just as a bit of a hint, when we're talking about the modulus of a complex number, we're really just talking about its absolute value. Or if we were to plot it in the complex plane, which is what we have right over here, what is its distance from the origin? So really, you need to find which of these complex numbers has a distance of 13 from the origin in the complex plane. Pause this video and see if you can figure that out.
Okay, I can't figure it out if I do not do the calculation to find each complex distance or absolute value of it. But it requires us to do some calculation, and it's not a hard problem, so I won't do that. Let's get into the next one. The absolute value and the angle of complex number. Did you ever heard about the concept that the complex number will have an angle. Did you ever heard about that? No. So let's get into that.
What I want to do in this video is make sure we're comfortable with ways to represent and visualize complex numbers. So you're probably familiar with the idea. Complex number, let's call it z. And z is the variable we do tend to use for complex numbers. Let's say that z is equal to a plus bi. We call it complex because it has a real part, and it has an imaginary part. And just so you're used to the notation, sometimes you'll see someone write the real part. Give me the real part of z. This is a function that you input a complex number and it'll output the real part. And in this case, the real part is equal to a. And you could have another function called the imaginary part. The imaginary part of z, you input some complex number, it'll output the imaginary part. The imaginary part, or it'll say how much you're scaling up I, and in this case it would be b. It would be b. This is a real number, but this tells us how much the I is scaled up in the complex number z right over there. Now, one way to visualize complex numbers, and this is actually a very helpful way of visualizing it when we start thinking about the roots of numbers, especially the complex roots, is using something called an Argand diagram. Argand diagram. So this is this. And so it looks a lot like the coordinate axes, and it is a coordinate axis. But instead of having an x and y axis, it has a real and imaginary axis. So in the example of z being a plus bi, we would plot it.
Okay, just remind me one thing. They call it imaginary than imaginary. I usually would say imaginary, but they call it imaginary.
Really is a position vector where you have the real part along the horizontal axis. So let's say this is a, and then the imaginary part along the vertical axis or the imaginary axis. So let's say that this is b. And so we would represent in an Argand diagram the vector z as a position vector that starts at 0 and that has a tip at the coordinate a comma b. So this right here is our complex number. This right here is a representation in our Argand diagram of the complex number a plus bi, or of z. Now when you draw it this way, when you draw it as a position vector, and if you're familiar with polar coordinates, you're probably thinking, hey, I don't have to represent this complex number just as kind of coordinates, just as an a plus bi. Maybe I could represent this as some angle here, Let's call that angle phi, and some distance here. Let's call that r, which is kind of the magnitude of this vector. And you could, if you gave some angle and some distance, that would also specify this point in a complex plane. And this is actually called the argument of the complex number, and this right here is called the magnitude, or sometimes the modulus, or the absolute value of the complex number. So let's think about it a little bit. Let's think about how we would actually calculate these values. So r, which is the modulus or the magnitude, it's denoted by the magnitude or the absolute value of z1. What's this going to be? Well, we have a right triangle here. This side is b, length b. The base right here has length a. So to calculate r, we could just use the Pythagorean Theorem. R squared is going to be equal to a squared plus b squared. Or r is going to be equal to the square root of a squared plus b squared. If we want to figure out the argument, let's say we want to figure out the argument, this is going to be equal to what? So let's think about this a little bit. We have b and a. So what trig function deals with the opposite side of an angle and the adjacent side? So let me write the famous SOHCAHTOA up here. SOHCAHTOA. Tangent deals with opposite over adjacent. So the tangent of this angle, which we call the argument of the complex number, the tangent of the argument is going to be equal to the opposite side over the adjacent side. It is equal to b over a.
So now I know why they call it arguments. But basically, it's not just one argument. It's two arguments. It's just like how can you define a function or something like that. Here we get the r, which is the distance of that complex number, right? Or the absolute value of that. Then we get this this angle, this is also one argument for the let's think it as a function, but actually it's not. But somehow it got two arguments. But for this case, they will just lovely to call this angle as the argument of this complex number. Weird definition.
And so if we wanted to solve for this argument, we would say that the argument is equal to the arctan, or the inverse tangent, of b over a. Now, if we wanted to represent, let's say we had the complex number, let's say that we were given the argument and the, let's say that we're given the modulus and the argument. Let's say we're given that. How do we go the other way? Right now, if we have the a's and the b's, the real and the complex part, I just showed you how to get the magnitude and how to get the angle, or the argument. But if you're given this, how do you go the other way? Well, here, if you're trying to figure out a given r and theta, so you're trying to figure out an adjacent side given an angle and the hypotenuse. So adjacent over hypotenuse is equal to cosine. So you would have cosine of the argument is equal to r is equal to the adjacent over the hypotenuse, is equal to a over r. Multiply both sides by r. You get r cosine of phi is equal to a. Do something very similar for b. If we use sine, opposite over hypotenuse, sine of the argument is equal to b over r, is equal to b over the magnitude. Multiply both sides by r. You get r sine of phi is equal to b. So how would we write this complex number? So this complex number z, the complex number z is going to be equal to its real part, which is r cosine of phi, plus the imaginary part times I, plus r, let me do that same green, plus r sine of phi times I. Now, this might pop out at you as something that's pretty interesting if you've ever seen Euler's formula. Let's factor out this r over here. So this is going to be equal to, factor out an r times cosine of phi, plus, I'll put the I out front, I sine of phi. I sine of phi. Now what is this?
Okay, wait a minute. Here, I just want to remind you one thing, which is how can you read this symbol? They call it phi. So you remember how you read it. You also call it phi. You read it as phi, F-I. That's it.
And if you've seen the videos, I do it in the Taylor series, a series of videos in the calculus playlist, and it's really one of the most profound results in all of mathematics. It still gives me chills. This is Euler's formula. This by Euler's formula is the same thing. This is the same thing, and we show it by looking at the Taylor series representations of e to the x and the Taylor series representations of cosine of x and sine of x. But this is, if we're dealing with radians, e to the I phi, e to the I phi. So z is going to be equal to r, times e to the I phi, So,
well, at this extent, you may do not understand why he represents or replaced the whole stuff by using the simple e to the I phi expression. Well, that's because he definitely made another video that we didn't say before. But the logic is the same. This expression could represent this long expression. It's somehow. So that's it. Don't think too much about it.
There's two ways to write a complex number. You could write it like this, where you have the real and the imaginary part. That's maybe what we're used to. Or we can write it in exponential form, where you have the modulus, or the magnitude, being multiplied by a complex exponential. We're going to see that this can be super useful, especially when we're trying to find roots. Now, just to make this tangible, let's actually do this with an actual example. So let's say that I had, let's say that I had z1 is equal to, let's say that z1 is equal to square root of, let's say it's square root of 3 over 2, plus I. And so we want to figure out its magnitude, and we want to figure out its argument. So let's do that. So the magnitude of z1 is going to be equal to the square root of this squared. So this is going to be equal to 3 over 4, 3/4, plus 1 squared, or I should say plus 4/4. plus 4/4. So this is going to be equal to square root of 7 over 4, which is equal to the square root of 7 over 2. And now let's figure out its argument. So let's draw, if I were to draw this on an Argand diagram, it would look like this. It's going to be in the first quadrant, so that's all I have to worry about. So let me draw it like this. And so we have a situation. So it's going to be square root of 3. Actually, let me change this up a little bit just so the numbers get a little bit cleaner. Sorry about this. Let me make it a little bit slightly cleaner. So just so that we have a slightly cleaner result, because we want to make our first example a simple one. So let's make the square root of 3 over 2 plus 1/2 I. So let's figure out the magnitude. The magnitude here, z1, is equal to the square root of square root of 3 over 2 squared is equal to 3 over 4 plus 1/2 squared is equal to 1/4. This makes things a lot nicer. This is equal to the square root of 1, which is 1. And now let's think about it. Let's draw it on an Argand diagram to visualize the argument. So this is my imaginary axis. That is my imaginary axis. This is my real axis, And so this complex number is square root of 3 over 2. Square root of 3 is like 1.7. So if we have like 1, it'll be like, so this is 1, it'll be like right over here, someplace right over here. This is square root of 3 over 2, the real part. The imaginary part is 1/2. So if this is 1, this is 1/2. The imaginary part is right over here, 1/2. And we actually also know its length. Its length or its magnitude is 1. So how do we figure out phi over here? We know that this side over here is square root of 3 over, oh, let me be careful. We know that side over there is 1/2. That's the imaginary part. And we know the base is square root of 3 over 2. So a bunch of ways we can do this. One, you could just do the tangent, because that involves the opposite over the adjacent. You could say that the tangent of phi is equal to the opposite, is equal to 1/2 over the square root of 3 over 2. And then you can take the inverse tan of both sides. So this would be the same thing as phi being equal to the inverse tangent, or the arctangent of, if you multiply the numerator and the denominator by 2, this is 1 over the square root of 3. You could do it like that. You could also say that phi is equal to the inverse sine of, so the sine of phi is going to be equal to the opposite over the hypotenuse. So sine of phi is equal to 1/2 over 1, or phi is equal to the arcsine of 1/2. And you could put that in your calculator. Or you could recognize this is a 30, 60, 90 triangle. This base right here is square root of 3 over 2. This is 1/2. This is 1. So this angle right here is going to be 30 degrees. And that's just from pattern matching from a 30, 60, 90 triangle. You could look at these and also get something similar. Now, I want to put this in radian form, because whenever I use the exponential form, you want it to be in radians. So phi is equal to 30 degrees. Phi is equal to 30 degrees, which is the same thing as pi over 6. So if I wanted to represent z1 in exponential form, it would be the exact same thing as r, or its magnitude, which is 1. I'll put the 1 out there, even though you really don't have to. 1 times e to the pi over 6i. E to the pi over 6i. And we're done. Exact same thing as r, or its magnitude, which is 1 times e to the pi over 6i. E to the pi over.
Now, just think about this. This is just another representation for the complex number writing here. You could write the whole thing instead of with the I, you could represent with the E. Okay, then we get a new concept. Maybe it's not new. It's called polar form.
Polar form of complex numbers.
Let's say that I have the complex number z, and in rectangular form, we can write it as -3 plus 2i. So first, let's think about where this is on the complex plane. So this is our imaginary axis, and that is our real axis. And let's see, the real part is -3. So we could go 1, 2, 3 to the left of the origin. Let me space that out a little bit more evenly. So 1, 2, 3 to the left of the origin. So -3. And then we have 2i. So we're going to go up 2. So up 2 in the imaginary direction. So 1, 2, just like that. And so z is real part -3, imaginary part 2, Z would be right over here in the complex plane. So that is Z right over there. Now what I want to think about are other ways to essentially specify the location of Z. And in particular, instead of giving the real and imaginary parts, essentially the coordinates here, let's think about giving a direction and a distance to get to Z. So for example, we could give the distance from the origin to Z. So let's call this distance r. But that distance by itself isn't enough to say where Z is. You have to say in what direction do you have to go a distance of r to get to Z. And so to specify the direction, we will have this angle theta in radians, this angle between the positive real axis and this line right over here, this line that, or the segment that connects the origin and Z. So if someone gave you this angle and this distance, then you could get to Z. Now what I want you to do right now is pause this video and see if you can find a relationship between r theta and -3 and 2. In fact, given this complex number in rectangular form, can you figure out what r and theta are? Well, let's think.
Okay, I know that. So basically, you can do it in this way. You could say that tangent zeta, it is equal to the upside over the adjacent side, which is 2, something like this. This is one way of represent it. But we also could say that the sine zeta equal to something and the cosine zeta equal to something. But for now, I won't cover that here.
Through this horizontal and vertical. And so what would the horizontal and vertical coordinates of this point be? We obviously know they're -3 and they're 2, but what would they be in terms of cosine theta and sine of theta? Well, look, this point right over here is a radius of 1 away from the origin. So this distance right over here, that distance right over here is 1. But now we are r away from the origin, where r times as far. So for r times as far in that direction, then we're going to be r times as far in the vertical direction and r times as far in the horizontal direction. We're going to have to scale we're going to scale everything by r. So the horizontal coordinate of this point right over here, instead of it being cosine of theta, it's going to be r times cosine of theta. So this point right over here, which we know is -3, is going to be equal to r cosine of theta. And by the same logic, this point over here, the vertical coordinate, we're going to scale up sine theta by r, where r times is far. So this point right over here is going to be r sine theta of the unit circle definition of trig functions, because we are going to use some trig functions to relate r theta and 2 and -3. So I'm going to construct a unit circle here. So construct a unit circle. So this right here is a unit circle, circle of radius 1. So construct a unit circle. That's a unit circle. So by definition, what are the horizontal and vertical coordinates of this point right over here, where this line intersects the unit circle? Well, this is forming an angle of theta with the positive real axis. And so the horizontal coordinate over here, by definition, is going to be cosine of theta. Cosine of theta. That's the unit circle definition of cosine of theta. And the vertical coordinate is going to be sine of theta. Sine of theta. And so what would the horizontal and vertical coordinates of this point be? We obviously know they're -3 and they're 2, but what would they be in terms of cosine theta and sine of theta? Well, look, this point right over here is a radius of 1 away from the origin. So this distance right over here, that distance right over here is 1. But now we are r away from the origin, where r times is far. So for r times as far in that direction, then we're going to be r times as far in the vertical direction and r times as far in the horizontal direction. We're going to have to scale we're going to scale everything by r. So the horizontal coordinate of this point right over here, instead of it being cosine of theta, it's going to be r times cosine of theta. So this point right over here, which we know is -3, is going to be equal to r cosine of theta. And by the same logic, this point over here, the vertical coordinate, we're going to scale up sine theta by r, where r times is far. So this point right over here is going to be r sine theta. And we already know that that's equal to 2, r sine theta. So given that, can we now figure out what r and theta are? So let's first think about figuring out what theta is. So to do that, let's think about some of our trig functions. So one trig function that involves sine theta and cosine theta is tangent theta. So for example, we could say tangent theta, tangent of our angle, tangent of theta is equal to sine of theta, is equal to sine of theta over cosine of theta, over cosine of theta. But we could also multiply the numerator and denominator here by r. That won't change the value. So that's the same thing as r sine theta over r cosine of theta. And we know r sine theta is going to be equal to 2. And we know that r cosine of theta is negative 3. So this whole thing is going to be negative 2/3. Another way of thinking about it is the tangent of this tangent of theta is going to be the same thing as the slope of this line right over here. And what's the slope of that line? Well, if you start at z and you want to go to the origin, you're going to go positive 3 in the x direction, and then you're going to go negative 2, or as you could say positive 3 in the horizontal direction, and then you go negative 2 in the vertical direction. So the slope is your change in vertical over change in horizontal. It's negative 2 over 3, negative 2 over 3. But now we can use this to solve for theta. To solve for theta, we just take the inverse tangent of both sides, and we get theta is equal to inverse tangent of negative 2/3 of this thing right over here. So let me copy and paste that, and we could get our calculator out to figure out what this actually is. So let's turn it on. Let me make sure that I am in radian mode. I am. And so I can take the inverse tangent of negative 2 divided by 3, which gets us negative 0.58800, on and on and on. So if we round to the nearest hundredth of a radian, it'd be negative 0.59. So this is approximately negative 0.59. Now, is this the right angle? Is this the theta? Is this the theta that we are looking for? Well, this theta, negative 0.59, that's going to get us over here. That's this angle right over here. That's what the inverse tangent gave us. And it makes sense because this ray is a continuation of this ray right over here. Together, they would form a line. It has the same slope. But that's not the theta that we are looking for. The theta that we are looking for is going in the opposite direction. It's halfway around the circle. So if we think in terms of radians, it's going to be this angle plus pi radians. So the theta that we're looking for isn't 0. It isn't going to be what our calculator gives us for this. It's going to be this value plus pi. So theta, the theta that we care about, is going to be negative 0.59 roughly plus pi. Let me say approximately, just because I have rounded right over here. So let's get the calculator out. So let's take our previous response, and that's just the previous answer, plus pi, because we're going to go in the opposite direction. So that gives us 2.
Okay, so here we go. We got this word, ANS. Back to before, when I was still in school, I have no idea what the ANS is, but now I know it, it's the answer. You say this is the power of, if you know the English very well, then everything is understandable.
Roughly 2.55 radians. So this is approximately 2.55 radians is our claim for what theta is. Now, does that make sense that this angle right over here is 2.55 radians? Well, this angle, if we go straight up, that's pi over 2 radians, and pi is 3.14, so that's going to be 1.57, right? 1 point something like that. And this is pi radians, so that's 3.14, 159, keep going on and on and on. So 2.55 is indeed in the right quadrant. So that is right. This is going to be an angle of 2.55 radians. Now we just have to figure out the length, what r is. And that we can just use the Pythagorean Theorem for. We could set up a right triangle. We know that this distance right over here is 2, because this distance right over here is 2. And we know that this distance is, the coordinate here is negative 3, but the distance here is just 3. So we know from the Pythagorean Theorem that r squared is equal to 2 squared, plus 3 squared, or that r is equal to the square root of 4 plus 9, which is 13. And so there we have it. We have negative 3. So we know r is equal to the square root of 13, and theta is 2.55 radians. So using that information, we can now rewrite z in terms of r and our theta. So now we can say that z is equal to, instead of negative 3, we can write it as r cosine theta. So we can rewrite it as square root of 13, square root of 13 times the cosine of theta, which is, we're saying theta is roughly 2.55 if we round to the nearest hundredths, plus 2, we already know is r sine of theta. So r is square root of 13, and then sine of theta, 2.55. And then all of this we could say, or all of this is going to be multiplied times I. And if we like to simplify it a little bit, or to kind of really make clear what the r is here, we could factor it out. So we could say that z is equal to square root of 13 times cosine of 2.55, and once again 2.55 is an approximation, so maybe I should say approximately equal to cosine of 2.55 plus, I'll throw the I in front, plus I times sine of 2.55. And so when I rewrote z in this format right over here, it makes it much clearer what the direction I have to go in is. The direction is 2.55 radians counterclockwise from the positive real axis. And it also says how far I need to go. I need to go square root of 13. So this essentially makes the polar, it makes it clearer how we get there in kind of a more, I guess you could say, polar mindset. And that's why this form of the complex number, writing it this way, is called rectangular form, while writing it this way is called polar form. I need to go.
Okay, how do he define it again? Here they call this one the regular form. That makes sense. This is definitely the original form. But for this one, they call it the polar form. Why? Because it contains the cosine and sine. I guess that's the reason. And also it uses let's say the distance to, let's say, represent the vector. No, let's say the complex number here. So what he uses is the angle and the distance to represent the same thing. That's why they call it polar form of that. At the beginning, the polar form, it is used in the navigation on the sea. I don't know if you know that or not, but I just want to point it out. And we can also somehow convert the polar form into the rectangular form.
We are told, consider the complex number z, which is equal to the square root of 17 times cosine of 346 degrees plus I sine of 346 degrees. And they ask us to plot z in the complex plane below. If necessary, round the point's coordinates to the nearest integer. So I encourage you to pause this video and at least think about where we would likely plot this complex number. All right, now let's work through it together. So when you look at it like this, you can see that what's being attempted is a conversion from polar form to rectangular form. And if we're thinking about polar form, we can think about the angle of this complex number, which is clearly 346 degrees. And so 346 degrees is about 14 degrees short of a full circle. So it would get us probably something around there. And then we also see what the magnitude or the modulus of the complex number is right over here. Square root of 17. Square root of 17 is a little bit more than 4, because 4 squared is 16. So if we go in this direction, let's see, that's going to be about 1, 2, 3, 4. We're going to go right about there. So if I were to just guess where this is going to put us, it's going to put us right around here, right around 4 minus 1i. But let's actually get a calculator out and see if this evaluates to roughly 4 minus 1i. So for the real part, let's go 346 degrees, and we're going to take the cosine of it, and then we're going to multiply that times the square root of 17. So times 17 square root, a little over 4, which is equal to that. Actually, yes, the real part does look almost exactly 4, especially if we are rounding to the nearest integer.
Okay, so it seems like we do not have to do that much transformation. This step just represents the regular, let's say the rectangular form, because it indeed has the real part and the imaginary parts. The only difference is that we are using the magnitude and the angle for it. We are using the magnitude and the angle angle to form this expression. That's the only difference between the polar and the rectangle and the rectangular form. And here's another section. It's called graphically multiplying the complex numbers. Well, I guess that's not that complex. It's like you are doing some operations with vectors. I don't know. Let's just get into it.
Suppose we multiply a complex number z by negative 3i, and they show us z right over here. Plot the point that represents the product of z and negative 3i. So pause this video and see if you can work through that. All right, now let's do it step by step. First, I want to think about where would 3z be? Well, 3z would have the same angle as z, but its absolute value, or its modulus, would be 3 times larger. So you'd be going in this direction, but it'd be 3 times further. So that's 1 times its modulus, that's 2 times its modulus, that's 3 times its modulus, or it's 3 times its absolute value. So 3z would be right over here. Now, what about negative 3z? Well, if you multiply it by a negative, it's just going to flip it around. You could think about it as flipping it at 180 degrees, but it's going to have the same modulus. So instead of being right over here at 3 in this direction, it's going to be 1, 2, 3 in this direction right over here. So that is negative 3z. And now, perhaps most interestingly, what happens when you multiply by I? So if we have negative 3i times z now, which is exactly what they want us to figure out. Well, let's think about what happens if you had 1 and if you multiplied it by I. So 1 times I becomes 1i, so it goes over there. What if you then took 1i and multiplied it by I? Well, then you have negative 1. What if you took negative 1 and you multiplied it by I? Well, then now you have negative 1i. So notice, every time we multiply by I, we are rotating by 90 degrees. So over here, if we take negative 3z and multiply it by I, you're just going to rotate 90 degrees, and you're going to get right over there. So this is negative 3i times z, which is exactly what we were looking for.
Okay, this is what he told us. If we multiply that number by I, which means at the graph, what it would be is to rotate the point by 90 degrees. All right, let's get into the next one. Multiplying complex numbers in polar form.
We're given 2 different complex numbers here, and we want to figure out what is the product. Pause this video and see if you can figure that out. All right, now let's work on this together. So we know from the form that it's written here that the modulus of w sub 1 is equal to 3, and we know that the argument of w sub 1 is equal to 330 degrees. And by the same line of reasoning, we know that the modulus of w sub 2 is equal to 2, and that the argument of w sub 2 is going to be equal to, we can see that right over here, 120 degrees. Now, when you multiply complex numbers, you could view as one transforming the other. We've seen this in multiple examples. So let's imagine that we are transforming w2 by multiplying it by w1. So what is going to happen? Well, let me write it here. So what's the resulting modulus of w1 times w2? Well, we're just going to scale up w2's modulus by w1's modulus. Or essentially, we're just going to multiply the two. So this is going to be equal to 6, 3 times 2. And then the argument of w sub 1 times w sub 2. If we start at w sub 2's argument, 120 degrees, and then we rotate it by w sub 1's argument, well, then you're going to add these two angles. That gets you to 450 degrees. So this is equal to 450 degrees, which is more than a complete rotation. And so if we wanted to give it an angle between 0 and 360 degrees, if we just subtract 360 from that, that is going to be equal to 90 degrees. And so we can rewrite this here, or we can rewrite the product as w sub 1 times w sub 2 is equal to its modulus, 6 times cosine of its argument, 90 degrees, plus I times sine of its argument.
Alright, it seems like if you want to get the product of two corner form expression, then what you could do is to first multiply or get the product of the two absolute value, which is a modular of that corner form complex number. Then for the angle, for the argument here, as I said, you do it differently. You just want to add them together to get a new value, and you can use that as the angle of the product complex number in a corner form. But what about the division?
So we're given these two complex numbers, and we want to know what w sub 1 divided by w sub 2 is. So pause this video and see if you can figure that out. All right, now let's work through this together. So the form that they've written this in, it actually makes it pretty straightforward to spot the modulus and the argument of each of these complex numbers. The modulus of w sub 1, we can see out here, is equal to 8, and the argument of w sub 1, we can see, is 4 pi over 3 if we're thinking in terms of radians. So 4 pi over 3 radians. And then similarly, for w sub 2, its modulus is equal to 2, and its argument is equal to 7 pi over 6. 7 pi over 6. Now, in many videos, we have talked about when you multiply one complex number by another, you're essentially transforming it. So you are going to scale the modulus of one by the modulus of the other, and you're going to rotate the argument of one by the argument of the other. I guess you could say you're going to add the angles. So another way to think about it is, if you have the modulus of w sub 1 divided by w sub 2, well, then you're just going to divide these moduli here. So this is just going to be 8 over 2, which is equal to 4. And then the argument of w sub 1 over w sub 2. This is, you could imagine you're starting at w sub 1, and then you are going to rotate it clockwise by w sub 2's argument. And so this is going to be 4 pi over 3 minus 7 pi over 6, and let's see what this is going to be.
Okay, it is exactly like what I guess it should be. So for the division, you're gonna do it differently. For the modular, you still do the division, but for the angle of that, you're gonna do a subtraction out there. Okay, we're almost done. Let's say here we got the last one that we're gonna go through is the fundamental theorem of algebra. So first one, let's get into it.
The fundamental theorem of algebra. Fundamental. I'll write it out. Theorem of algebra tells us that if we have an nth degree polynomial, so let's write it out. So let's say I have the function p of x, and it's defined by an nth degree polynomial. So let's say it's a x to the n plus b x to the n minus 1, and you just go all the way to some constant term at the end. So this is an nth degree polynomial. The fundamental theorem of algebra tells us that this nth degree polynomial is going to have n roots. Or another way to think about it, there are going to be exactly n values for x, which will make this polynomial, make this expression on the right, be equal to 0. So at first you might say, okay, that makes sense. You've seen second degree polynomials whose graphs might look something like this. So let's say that's the y-axis, that's the x-axis. We know a second degree polynomial would define a parabola. So it might look something like this. And you could buy that. Okay, this is a second degree. That's second degree. And you see that this function equals 0 exactly 2 places. It has exactly 2 roots. It has 2 roots. So that's
okay. Here the roots means that there has some y value that there has some x values that could make the y or the result to be 0. That's how they define the roots.
Seems consistent with the fundamental theorem of algebra. And you could also imagine a third degree polynomial looking like this. So that's my y-axis. This is my x-axis. You could imagine a third degree polynomial looking something like this. bam, 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 and it just keeps going. And here you see it's third degree polynomial, and you'll see it has 1, 2, 3 roots. And I could have a fourth degree polynomial that maybe it looks something like this, where it goes something like this. And you say, okay, that makes sense. It'll have 1, 2, 3, 4 roots. But then you might start to remember things that don't always behave in this way. For example, many times we've seen parabolas, we've seen second degree polynomials that look more like this, where they don't seem to intersect the x-axis. So this seems to conflict with the fundamental theorem of algebra. The fundamental theorem of algebra says if we have a second degree polynomial, then we should have exactly 2 roots. Now this is the key. The fundamental theorem of algebra, it extends our number system. We're not just talking about real roots, we're talking about complex roots. And in particular, the fundamental theorem of algebra allows even these coefficients to be complex. And so when we're looking at these first examples, these were all real roots, and real numbers are a subset of complex numbers. So here you had 2 real roots, here you had 3 real roots, in this orange function you had 4 real roots. In this yellow function, this yellow parabola right over here, the second degree polynomial, we have no real roots. That's why you don't see it intersecting the x-axis. But we will have 2 complex roots. So this one right over here will have 2 complex roots. And the complex roots, the non-real complex roots, because really real numbers are a subset of complex numbers, these always come in pairs. And we'll see that in future videos. So for example, if you have a third degree polynomial, it might look something like this. A third degree polynomial might look something like this, where it has 1 real root, but then the fundamental theorem of algebra tells us it necessarily has 2 other roots because it is a third degree. So we know that the other 2 roots must be non-real complex roots. Now, could you have a situation where you have a third degree polynomial with 3 complex roots? So can you have 3 non-real complex roots? Is this possible for a third degree polynomial? Well, the answer is no, because complex roots, as we'll see in the next few videos, always come in pairs. That they're coming in pairs where they are conjugates of each other. So you could have a fourth degree polynomial that has no real roots. For example, something might look something like this. In this case, you would have 2 pairs of complex roots, or you would have 4 non-real complex roots, and you could group them into 2 pairs where in each pair you have conjugates, and we'll see that in the next video.
I don't know what's the point of this video, because even if we know how many roots an expression should have, that doesn't solve any problem. Okay, let's get into the next video.
Let's say that we have the function f of x being defined by the second degree polynomial 5x squared plus 6x plus 5. The fundamental theorem of algebra tells us that because this is a second degree polynomial, we are going to have exactly 2 roots. Or another way of thinking about it, there's exactly 2 values for x that will make f of x equal 0. So I encourage you to pause this video and try to figure out what those 2 values of x are. So if we're looking for the x values that would make this expression equal to 0, that's essentially trying to solve this equation. At 5x squared plus 6x plus 5 is equal to 0. And there's no obvious way I can think of factoring this right over here, so I'll just resort to the quadratic formula. So the quadratic formula tells us that x, where x is a solution to this equation, is going to be equal to negative b. I'll try to color code it. Negative b. This is b right over here. Negative b, so negative 6, plus or minus the square root of b squared minus 4 times a times A times C times A times C. All of that over 2 times A. All of that over 2 times A. So what does this simplify to? This is going to be equal to, so let me go back to this is going to be equal to -6. I'll try to keep it color-coded still. -6 plus or minus the square root. Now what is this going to be equal to? This is 36 minus 100. So -64, all of that over 2 times 5. All of that over 10. Now this is interesting. We are trying to take the square root of a negative number. Or another way of thinking about it, b squared minus 4ac is less than 0. b squared minus 4ac, which is oftentimes called the discriminant of this quadratic. This is less than 0. So if this is less than 0, this part of the quadratic formula, we're going to try to take the square root of a negative number. This is going to be a negative number. So we're going to result in an imaginary number. And so what that gives us are not 2 real roots, but 2 non-real complex roots. So this is going to be equal to -6 plus or minus 8i. 8i, the square root of -64 is 8i if we extend the principal square root function to imaginary numbers or complex numbers. All of that over 10. Or we could say x is equal to, let's see, if we find a greatest common divisor, if we try to reduce this, so we're going to have, let's see, they're all divisible by 2. So it's -3 over 5. That's the same thing as -6 over 10. Plus or minus 4 over 5, 4 over 5i. Or you could say that the 2 roots, which are non-real complex roots, so it's x.
Okay, here I just want to point out 2 things. The first one is, when I was still in school, they often, the stupid teacher always try to tell you that you could use some strategies to get the results for this kind of expression, but I found that that's not true. You definitely do not want to always find a strategy because it's very hard to find the right strategy. But what you could do is always use use a zeroing, or let's say the row. For example, this one, -b plus or minus the square root of b squared minus 4ac, the whole stuff divided by 2a. You always want to use this one to calculate out the root for this equation or expression. That's the most straightforward way and reliable way for calculating out the root value. That's the first step that I want to say. And the second step is, the second tab for it is, it seems like we could indeed find out the value of let's say the square root of a negative number. We can find the value of that. The only thing that we have to know is that if we want to find out the square root of a negative value, the result should be an imaginary number or a complex number.
X is equal to -3/5 plus 4/5 I, that's one of the roots, and then the other root is x is equal to -3/5 minus 4/5 I. Notice, we satisfied the fundamental theorem of algebra. We have 2 roots. They're non-real, but that fundamental theorem of algebra says, hey, look, we're just going to have, at least if we have nth degree polynomial, we're going to have n complex roots. They could be real or they could be non-real, and we see that right over there. We also see that they are conjugates. And the quadratic formula kind of sets up a situation where we are, especially if this ends up being less than 0, and so this, when you take the square root, you get an imaginary number, you see where those conjugates appear. Now let's verify graphically that this is indeed the case, that this does not have any real roots. So let's get a calculator out. So let me go into graph mode. So y is equal to, let me clear what I must have been doing out here before. So y1 is equal to 5 times x squared plus 6x plus 5. And then let me set a reasonable range here. So I don't know. Actually, I know very little about this function right over here. So I'm going to set a minimum range. I don't know, -10, x max, I don't know, +10, x scale is 1. Let's see, y max. Let's see, this thing actually does get pretty big pretty fast. So let's say y max is, I don't know, the y scale, I don't know, I'll say 100. 100. the scale, I'll make it 10. Each of those notches are going to be 10. Y minimum. Well, we want to see the x-axis to make sure it doesn't cross it. So let's go at negative, I don't know, negative 20. And now let's graph this. I'm hoping that I've actually captured it, and I have. So there you have it. You see that this thing does not intersect the x-axis. And in fact, we could zoom in on it. Let's see, it's a little bit hard to. It's a little, actually, let me just change the range a little bit. So let me just change the range. So let's make our x min, let's make it 5. Let's make our x max, whoops, not 50. Let's make that 5. And let's make negative 5 and positive 5. And then let's see, let's make our y max, let's make our y max equal to 20. And then our y scale, I don't know, we can make it 2. Okay, I think this will get us much closer in to, there we see. It does not intersect the x-axis. This does not have any real roots, but it has two non-real complex roots.
Okay, interesting. It seems like we just learned some new. Alright, in the end, we are going to get into the last video, which will end all today's learning. Let's get into it.
So we have a polynomial right over here. We have a function p of x defined by this polynomial. It's clearly a 7th degree polynomial. And what I want to do is think about what are the possible number of real roots for this polynomial right over here. So what are the possible number of real roots? For example, could you have 9 real roots? And so I encourage you to pause this video and think about what are all the possible number of real roots. So I'm assuming you've given a go at it. So the fundamental theorem of algebra tells us that we are definitely going to have 7 roots, some of which could be actually real. So we're definitely not going to have 8 or 9 or 10 real roots. At most, we're going to have 7 real roots. So possible number of real roots. So possible, let me write this down, possible number of real roots. Well, 7 is a possibility. If you graph this out, it could potentially intersect the x-axis 7 times. Now, would it be possible to have 6 real roots? Is 6 real roots a possibility? Is this a possibility? Well, let's think about what that would imply about the non-real complex roots. If you have 6 real, actually, let's do it this way. Let me write it this way. So real roots, real, and then non-real, complex. The reason why I'm not just saying complex is because real numbers are a subset of complex numbers, but this is being clear that you're talking about complex numbers that are not real. So you could have 7 real roots, and then you would have no non-real roots, and so this is absolutely possible. Now, could you have 6 real roots, in which case that would imply that you have 1 non-real root? Well, no, you can't have this because the non-real complex roots come in pairs, conjugate pairs. So you're always going to have an even number of non-real complex roots. So you can't just have 1. So let's rule that out. Now, what about having 5 real roots? That means that you would have 2 non-real complex adding up to 7. And that, of course, is possible because now you have a pair here. So I think you're starting to see a pattern. Essentially, you can have an odd number of real roots up to and including 7. So, for example, this is possible, and I could just keep going. I could have, 4 and 3. This is not possible because I have an odd number here. You're going to have an even number of non-real complex roots. So rule that out. But then if we go to 3 and 4, this is absolutely possible. You have 2 pairs of non-real complex roots. And then
Alright, so this video is just wanna try to tell us that we can only have the even number of non-real complex roots, and that's all. So it ends up today's learning very well, and I hope you enjoy this video. I will see you guys in the next one. Bye.